All right, class. Here I am doing my roller coaster data collection. Now, my hat looks stupid. My hypothesis was similar to many of yours. I hypothesized that this marble would be losing energy because friction was going to take some of that energy as it came down these slopes. So that means I think the velocity, the final velocity of the marble for each run of the roller coaster, each slope, is going to be slightly lower than the one that I can calculate with the energy equations. So here you see these lines. I have figured out the height of each slope. I have used a tape measure here, a sewing tape measure actually, to measure this distance here, from here to here in each slope, in meters. And I'm going to use that to find the average velocity in meters per second. I'm going to multiply that by 2 in my Google Sheet to find the final velocity of the marble on each slope independently. And then I'm going to use the energy equations, the square root of 2 times acceleration due to gravity for all objects on Earth in the absence of air resistance, which is 9.8, times the height of each of my slopes, like this one here, is in 0.58 meters, the height of each slope in meters. And I'm hypothesizing that my velocity from the runs is going to be lower than the velocity from the calculation. So let us begin. Trial 1, slope 1. All right, I'm going to hit start on the stopwatch as soon as I release the marble. And then I'm going to hit stop when it gets to the bottom of the slope. And I'm going to do it 10 times for each slope and enter it into my data section. Cool. Dun, 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 dun. Dun, 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 dun. Stopwatch. Dun, 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 dun. All right. Wow. 0.35 seconds. All right, let's do it again. Hmm, 0.31 seconds. Hmm, 0.63. 0.32 seconds. I didn't reset it. .26 seconds. I feel like that might be closer to the truth. Not really sure. All right. 0.3 seconds, maybe not. These are all falling pretty close to each other. 0.38 seconds. 0.26 seconds. 0.22. Huh. We got 10 marbles. That's pretty smart. .26 again. And finally, my last for the first slope, 0.35. All right, slope 2. Here we go. Yep. I'm going to leave these marbles down here as something that will stop my marble, hopefully. No, that's dumb. I'm not doing that. Never mind. They're going to get in the way. Ooh, 0.56. That was interesting. Shoot. All right. Hey team, I'm noticing something in the second slope. If you look at my slope, it appears to be curved within the context of the slope, and acceleration on it appears not to be constant. I'm not going to let this bother me. I'm just going to write about it in my error analysis section. Alrighty. So I've recorded my slope height, which is a straight line up to the top of the slope from the base of the slope, and then the distance, which is the diagonal course that the marble runs. So my velocity, of course, is going to be this displacement on the diagonal line that the ball is traveling on divided by the time it takes to travel there. Now, none of these numbers should change. That's too many decimals. I'm going to get rid of those. None of these numbers should change in response to, none of the distances here should change. The height and the distance the ball travels are the same between trials. 2 times the average velocity should be 2 times that number there. And then my predicted velocity should be the same through every single one of these, actually, in meters per second. My predicted final velocity. So this here, my average is going to be what I want to compare that to. And it looks pretty bad for me. It looks like my hypothesis on this first steep slope was not verified. Circular dependency. What is that there? Equals average. F2 to F11. I included the average within itself. My final velocity was faster than should have been possible given the energy equations. All right, let's do this one. Average velocity here is the displacement divided by the time equals the distance downslope or displacement divided by the time. Boom. All right, too many decimals. That. Is this the right equation here? The square root of 2 times 9.8 times B2, which is my slope height. Damn it, that's right. And this one is also working. Dang, I must just suck at data. That would be times J2. That's also correct. I don't like that. There's too many decimals here. I don't really know that to that accuracy. Get rid of this. Cool. Well, what have we here? Let's see. Zoop. All right. Compare 2 times that is that. This one looks a little better. This one verifies my hypothesis. Oh, what a conundrum. What a conundrum that is. All right, here we go. Average velocity equals displacement that it's traveling divided by the amount of time it takes. Enter. Too many decimals. Let's grab all these. Too many decimals. No, thank you. Great. Pull this bugger down. Pull this bugger down. Well, this one looks good too. Nothing even came close to. So my calculated average velocity is not close to predicted there, so I lost some energy in that one. Nice. So I got some things I can compare. my final calculated velocity should be compared with my predicted slope velocity. And according to my hypothesis, because of friction, each of my average velocities should be lower than the velocity predicted with the energy equations given the height of the slope. So, I don't know how I'm going to write this hypothesis. 2 out of 3 verify and 1 refutes. I guess I'm going to have to calculate my error. Okie dokie. So I'm on my last steps here with my data analysis. And I've taken my average of my final average velocity, which was from the measured time, and then multiplied by 2, given the equations we derived to find final velocity of an object starting at rest at constant acceleration. Okay, I've got that there. Then I found my minimum of that calculated column and my maximum, and I used the one that was the furthest outlier to calculate my precision percent error using this equation, where it was furthest outlier minus average divided by average times 100. We've used that a lot, okay? And so I got a precision percent error. Now, in addition to that, this average final velocity I want to compare to my predicted velocities. Now, I said they'd be lower. This one's higher. All right. This one, average, is lower. Cool. And this average here, this last one is, whoops. Wait, where is it? And this last one, this last average here, velocity is lower than that. So I made a table comparing those here. And I distinguished what was what on the thing. And I got this beautiful graph here that allows me to easily assess my hypothesis. Although apparently I use capital letters sometimes in lowercase. Oh, well, whatever. Okay. Now, the next thing I'm going to want to do is make a graph of my precision percent errors. All right, so there we go. Precision percent errors accomplished. And I want a graph of this, probably. So I'm going to go to my chart editor here. I'm going to insert a chart. I don't like that. Yeah, I want to change that. I want a bar. Just give me a bar graph. There we go. There we go. I can look at that. Nice. All right. Well, I'm ready to write a data section. That's neat. And that only took me 20 minutes. All told.